Hi, this is Christopher Richardson, the founder of Power Induced Design. If you're watching this video, then you probably saw the previous one about charging. If your batteries are charged, like mine are from making that last video, then you're ready to power something with them. In this segment, I'll talk about how much current you can draw, how low you can let each cell's voltage reach before you should stop, and how hot you can let your batteries get, assuming you want maximum battery life. As with charging, the best and safest course is to have a circuit that balances the voltage across series stacks or the current from each cell in parallel stacks, especially if the batteries are not the same age. Now, in all honesty, it's unlikely to have a stack with some worn-out cells and some new ones, but the closer you run to the voltage and current limits, the more important it is to have those protections in place. Here are some still images from my thermal camera showing two cells in series, or a 2S1P pack at various currents. Here's 1 amp discharge, now 2 amps, 3 amps, and this is about the limit of what I'm comfortable with. The ignition temperature for cobalt cathode batteries is around 130 degrees C, but neither you nor I want to be anywhere near there. It's not enough to just keep your batteries from overheating themselves during charging and discharging. They need to be protected or isolated from other heat sources too. In my design, the PCB itself and perhaps 1 to 2 millimeters of air separate the battery on the left from the heat of the linear regulator that charges the battery. The battery on the right suffers more when the batteries are in use, as there are two switching regulators there that are efficient but certainly do generate some heat. Alright, so I've transferred batteries 2 and 5 to the actual charger circuit, so it's going to very gently charge them the way it's supposed to. While I'm doing that, I'm actually testing batteries 3 and 4, which finished charging at a discharge rate of 2 amps. So open circuit, they were about 8.27. As soon as I started drawing 2 amps, it dropped to about 7.2 or so. And I'm using my electronic loads battery capacity function to actually check, so I'll have a nice graph to show of voltage and current over time, and then it will calculate battery capacity for me. For my nameless orphan 18650 cells, whose capacity has now dropped to around 1500 milliamp hours, I'm not willing to draw more than about 3 amps. I did try a test at 4 amps, and the stack voltage fell to 5.8 volts, the safety limit, in under 5 minutes. Now, I've seen some lithium-ion batteries discharge to 2.7 volts or even 2.5 volts per cell, and that may be okay for newer technology or when battery life isn't as important. For my purposes, though, I stick to a cutoff of 2.9 volts per cell. I was a bit surprised to see that these old batteries still had plenty of capacity left, but being old, they have higher internal resistance, making their terminal voltage drop more than new batteries would. Despite their age, and yes, some abuse by me, they do a pretty good job of keeping their amp hours stable at different discharge rates, losing only a little bit of capacity at higher discharge currents. As a final note, these old batteries and the circuits I've shown are personal projects, used in my lab and never far from my specialty fire extinguisher. If I were designing a commercial product, I would use the so-called protected 18650 cells. As the name suggests, these are batteries with built-in circuits that shut off if the battery charge current or discharge current go too high, if the battery voltage goes too high during charging or too low during discharging, and last but not least, if the battery temperature rises too high or drops too low.